Okay, hi. So let's finish up Unit 4. There'll be this lecture and then a really small lecture that is going to be attached to this one about expected value. But this is kind of the big one. This is where everything we've done so far in Unit 4 kind of all comes together, okay? And what we'll be doing is like bigger questions that have us put counting and probability together to solve larger problems. So let's see what we got. All right, now remember that there's two main things we need to concern ourselves with. Number one is the situation we're dealing with choices with or without replacement? In other words, is it something that when we take our choice out, that it changes the pool of choices for the next person? Or does our choice not matter and whatever we choose, we put back in? Okay, so that kind of goes back to our early talk about probability. When we first started doing probability, we talked about things with replacement. We were talking about drawing a card from a deck, but replacing that card and drawing a second card out of the deck. That was with replacement. Or choosing uh, dice, right? When you roll a dice, you can't take one of the sides off. It's always going to be those six choices no matter what. That is with replacement. And when you have replacement, then you get to do the multiplication thing. You get to multiply the two choices together. Now, when we deal without replacement, then that gets a little picky, and that goes back to what we talked about in the last lecture. That's when we have to kind of drill down and we have to decide from carefully reading the problem and reasoning it out, we have to decide, does order matter here or doesn't order matter here? Okay. And that brought us to the two different kinds of problems and the two different formulas that we were able to use on our calculators, right? We had the NPR and the NCR. And remember that this is just the weird notation that my software I use has to use, but this is what it looks like on your calculator. And remember, you use the NCR when you not care. Right? And if you look at it and you read it from left to right, you can see this like no care, you don't care, not care, we don't care. Over here, that's the other one. That's how I keep it straight. Anyway, let's just review these problems real quick before we start to lean on this and put that original probability kind of idea together. Okay. So let's do this first example. It says a baby shower has 19 people in attendance and there are five prizes. $150, $100, $50, $25, and $15. How many choices for the winners of the prizes if they are drawn from smallest to largest prize? Okay. So first off, it specifically says drawn from largest to smallest. So that indicates that there's some sort of order that's important. Okay. But also you could infer from the fact that the prizes range from $150 to $15 that people would probably prefer to get a $150 prize versus the $15 prize. Okay. So that tells us that order does matter. So does the order matter? Yes, and when order matters, we use the NPR. All right. Here, our N is the total number is 19, and our R is the number of choices we're going to make is going to be 5. So we'll say 5P, sorry, not 5, my bad, 19P5. Put that in our calculator and we get 1,395,360. Let me remind you how to put that in your calculator. After you've written it like this, you're going to want to put in the 19 and then you're going to say math and you're going to enter over 3 times to probability. And then you're going to go down twice to the NPR. And I'll show you here. We're going to go math, and we're going to put in the 19 first. Math over to probability, down to NPR, enter, and then we're going to fill in that next number. This will be 5 and hit enter, and that's our number, okay? And don't forget, please, to write your answers in a complete sentence. The total choices would be 1,395,360. All right, awesome. Let's look at the next one. The next one says a baby shower has 19 in attendance and there are 5 prizes. How many choices are there for the winners? So in this case, 5 prizes indicated that they'll be the same prize, and we're not choosing the prizes in order of the highest to the lowest or whatever. It's just 5 random people being chosen for the prizes here. So does the order matter? No. And when the order doesn't matter, we no care. We use the NCR. Okay. Here again, our N is equal to 19 and our R is equal to 5. But when we check this out, when we set this up, you're going to see, even though it seems like that's the same question, of course, this is why it's important for you to know if the order matters or the order doesn't matter, because that gives us a completely different number, 11,628. So there are 11,628 ways to choose the 5 winners. Okay. Awesome. All right, so let's start talking about mixing counting with probability. Okay, so we spent all that time on the counting and I reviewed counting with you here, because we're going to use that as basically the numerator in a probability question. Okay, so we didn't do any probability last time. We were just counting, but in lecture 1 of unit 4, we did basic probability, and in unit 2, lecture 2, in unit 4, we did all that conditional probability. So we're going to go back to that idea of probability and having to write the answer as a sentence and a percentage and stuff like that. So here are some guidelines. Find the total number of choices depending on whether the order matters or not. Okay, and that is for the event. Find the choices for the or the total amount of choices, and then we'll also find the choices for the determined event, depending on whether or not the order matters. And then we'll find the probability. And remember, the probability of the event is the number of ways it can happen over the total number of ways all of it can happen. So choices of the event over the total number of choices. And then finally, we'll describe it as a percentage, and give us a nice sentence and convert it from a probability to a percentage. So let's get started with the first one. Now, before I get started, let me give you today's silly phrase. And today's silly phrase is my cactus just joined a rock band. Okay, my cactus just joined a rock band. All right, so let's get back to the example here. Now, it's really, really important for you to read all this stuff really critically. I know you're probably tired of hearing me say that, I know I'm almost tired of saying it, but it bears repeating, right? It's just super important. I'm going to say it again. You have to read this really, really critically. And these questions are tricky because you have to read it critically and you have to make some decisions here. So let's take a look. You own 16 PlayStation games and you want to randomly arrange 5 of them on a rack. And we want to know what's the probability that the rack ends up in alphabetical order. Okay. You've got your 19 games here and you're closing your eyes and you're pulling this one and sticking it on the rack and pulling this one and putting it in the next place on the rack and so forth 5 times. And the question is, what is the chance? What's the probability that when you opened your eyes, all of those would be in alphabetical order? It sounds kind of crazy, huh? Okay. So, this is where it gets a little bit tricky. And I always have to explain this part to everyone. There's only one way to get alphabetical order. Okay? There's only really one way. Okay? And order matters. So we're definitely wanting to know, are the choices with replacement or without replacement? And all of this is without replacement. The event, which is the alphabetical order, and the total, which is the ways to choose 5. Those are the two things, and they're both without replacement. Okay. Now, does the order matter? Order does matter because it's alphabetical order. There's no other alphabetical order to choose from, right? We have our A, B, C, D, E, F, G, blah, 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 right? We don't have one that is A, B, C, F, G, D, E. It doesn't go in that order. There's only one alphabetical order. Okay, so does order matter? Yes. And because order matters, we're going to use NPR. All right. Now, let's put the little pieces together. Okay. So what is the total? The total is going to be 19. Not 19, my bad. 16. My brain's on 19. Okay. It's going to be 16, choose 5. That is going to give us the total number of choices. Okay. And when we compute that, that is 524,160. Okay. Now we need to figure out the event. And the event is, and what is the event? Well, the event is choosing from the 5 we chose. Okay, so hear me out. From the 5 we chose, what's the probability that all 5 of them are in alphabetical order? So this is from the 5 we chose. We want all 5 to be in alphabetical order. All right. And so when we run that, it is equal to 120. Now, to finish this up, we want the probability that the 5 games are in alphabetical order. That is going to be the probability of the event, or not the probability of the event. Let me not say that. Let me just say it's going to be the event over the total, just like it was before. And in this case, it's going to be 120 over 524, 160. And when we do that math there, we get 2.29 e to the -4. And let's write that out, 0.000229. And then if we turn it into a percentage, we can say the chance that the games are in alphabetical order is 0.0229%. And if you're ever like, God, how do I say that? Remember that is tenths, hundredths, thousandths, 10,000. So it's 223 hundred thousandths of a chance. We're talking about 100,000th of a chance. So if you ever have that happen, there's something special. Anyway, okay. All right, so let's just review real quick. You've got to decide first off if the events are with or without replacement. Sometimes the total could be without replacement, and I'll do an example like that. Usually they're both without replacement, but sometimes you might have a little flippy floppy. Okay, so just be aware. Okay, let's take a look at the next question. The United States Senate Appropriation Committee consists of 29 members, 15 Republicans, and 14 Democrats. The Defense Subcommittee consists of 10 Republicans and 9 Democrats. How many ways can the members of the Defense Subcommittee be chosen from the 29 senators on the Appropriations Committee? So let's go back there. It says, how many ways can the members of the Defense Subcommittee be chosen? This is not a question asking for probability. This straight up says, what's the probability? This question is just simply asking us to figure out how many ways we can do this. Now there's choices in 2 different committees. Let's just call in here. So let's answer these questions here. Are the choices with replacement or without replacement? So in other words, when you choose someone from either side, let's say the Republicans, we choose Republican out, right? Do we throw them back in and can we choose them again? Can one person hold 2 seats? No. So this is without replacement, okay? Does the order matter? This is not ranked. And I say the order does not matter because we're just choosing members, not like president, vice president, etc., something with rank. Okay, this is non-ranking, so order does not matter. So we're going to use NPR. Okay, now let's get back to the question here. Looks like we've got two of them to do. We've got a Republican situation, and we've got a Democrat situation. So we need to handle each one of those. Now, remember that this question is asking us just how many ways. That's all it's saying is how many ways. So this is just a counting problem. All right. So first let's do those the Republicans here. That would be 15 P, and how many do the Republicans get to choose? 10. And then let's write out our Democrats here. We've got 14 P9, right? Those are the numbers that we were given here. And when we do that math for the Dems, we've got 2,002 ways to just choose the 9 out of the 14. And there are 3,003 ways to choose the 10 from the 15, but it asks us the total. And so total ways is just how many are there? This is just like soup and entree question. This is like a soup and an entree question. We're just going to multiply it together to decide how many ways, how many total ways. So we're going to say 3,003 times 2,002. That's going to give us 6,012,006. So there are, oops, sorry, there's some more stuff down there I wrote earlier. There are 6,012,006 ways to choose the subcommittee. I forgot what I was writing. I'm sorry. All right. Okay, let's keep on going here on my mouse. All right, so I kind of wrote down little steps here for finding the probability. And let's look at this next question here. A 4-digit PIN number is selected. What is the probability that there are no repeated digits? Okay. Now, first off, it says that it's a 4-digit PIN. And I don't know about you, but I know that PIN numbers can have repeated digits in them. Okay. And then it asks the question, the event is, what's the probability that there are no repeated digits? So, if in breaking this down here, we can see that there could be repeated digits. So the total is with replacement, and the event is without replacement, okay? So you really have to look at these two things completely separate. Again, as I said, you got to really kind of critically read these problems. They're not going to intuitively, the answer's not going to probably intuitively jump out at you. You just need to kind of read it and think about it, look back at some examples, and stuff like that. All right, so let's look back at this question. Now, we have to put two things together. I'm sorry. Ooh, we have to put two things together here. We need to know the total. We need to figure out what the total is. So the total number of choices. And that is going to be the total. This is the total ways to get a four-digit PIN number. Okay. Now, there's a couple of different ways we could think about this, but I think the easiest way is to just kind of like lay it out. Now, how many digits are there? I always have students say 9, but there's not 9 digits. There's 10 digits, right? There's 10 digits. And I don't mean that we're counting 10. We got to start with 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the digits, okay? So we're talking about the first digit. How many ways, how many different numbers can fit in that slot? Well, there would be 10 different numbers that could fit in that slot. And because we can have repeats, that's not what we're looking for, but because we can have repeats, if not, why would they be asking this question? Okay, use some logic. Because they can be repeats, then there are 10 options for that second number, and there are 10 options for that third number, and in fact, there's 10 options for that fourth number. So the total here is going to be 10 to the power of 4. Now let's look at the event. All right, now, does the order matter? No, the order doesn't matter. The order doesn't matter because it just said no repeats. That has nothing to do with the order of which the digits come out. So, does the order matter? No. NPR is what we're going to use. So the event, let's say what the event is. The event is that the PIN number has no repeats. Okay, like, you go to the bank, you get a new bank card or whatever, and then they, assign you a PIN number. And, there's a chance you could have a repeat digit in that PIN number. There's a chance that you don't. I've certainly had them both ways. Okay, so let's see how this is going to go. Well, we have 10 digits to choose from, choosing 4. So this is what we're going to do. This is our calculation, 10P4. That's going to give us 5,040. And then remember our final thing here is we're looking for the probability that the PIN number chosen has no repeats. Okay. So when we put that together, we have 5040 over 10 to the 4th power. That's going to give us 0.5040. which is 50.4% chance that the PIN number has no repeats. Okay. Let's take it a look at another one. Hold on a second. I really need a drink of my soda. All right. Exercise 6. A certain state's lottery pays out $1 million if their 6 numbers match the 6 numbers drawn by the Lottery Commission. Okay. So very, very similar to there being only one alphabetical order. There's also only one way your numbers can all line up with the Lottery Commission. Okay. The balls are numbered between 1 and 48 and are not ranked. Okay. Compute your probability of winning that 1 million if you purchased a single ticket. So this is literally what we're going to do. We're going to compute what your probability of winning $1 million with a lottery in this kind of situation. We're not talking Powerball. We're not talking pick four. This is just literally a very simple little example. Okay. Now, we still have to ask our questions. Are our choices with replacement or without replacement? Now, if you've ever watched them draw the lottery, you know that the little thing comes up, thump, and a little ball comes up, and they remove the ball from all the other numbers that are floating around, and then thump, comes the second ball. They don't ever put the ball back in. So this is definitely without replacement. Okay. Does the order matter? I believe it does not matter. It says that they are not ranked. So in other words, they don't have to be pulled in the exact, say, numerical order or whatever. Are not ranked. Okay. So order, does the order matter? No. So we're going to use the NCR option. Okay. All right. Now, what do we need to know? We need to know the total. And we need to know the event. So let's look at the total. And the total is we have 48 C, and how many are we choosing? 6. So 48 C6. And then our event is of the 6 numbers chosen, are they the ones to match the Lotto Commission? There's only one way to do this. So there's only one way to do this, and all 6 have to match, okay? And that makes sense. And you're probably like, duh, of course, Dr. Kelly, of course we know that. Yeah. Okay, but I'm just making a lot of stink about it because it's a confusing point. All right. So when we set this up, that means that of these 6 that we chose, 6 were right. Okay. Now let's do that here. Let's 6 math over to probability down to choose 6. Oh, 1. Because there's only one way that that can work. They have to all match. And if order doesn't matter, there's only one way. If order doesn't matter, that means that the 6 numbers that I chose have to be the same 6 numbers that they chose. If order matters, then there's a whole lot of other options, because what if I chose the 3rd number and they chose it first or some crap like that? So when order doesn't matter, there's only one way to do something. Okay, so let's look at our probability. And so here we're looking for the probability that we win $1 million. Okay, or get all 6 numbers. That's the same thing as winning $1 million, right? And that's going to be 6, choose 6 over 48, choose 6. And I wrote it like this because I wanted to show you how to put this in your calculator like this if you wanted to. Of course, if you knew that using the combinatorics with the same number gives you an answer of 1, then congratulations, and that's great. But I'm going to act like we don't know that. So I'm going to put it in just how I see it here. 6 math over here to probability down to the choose, enter in the 6. Now here you have to be careful because if you keep on typing, you'll be down here in this subscript. You have to come over here and get back up. Got to get out of that down there and like the sub exponent. You got to get back up, right? And then we're going to divide by, and then this is 48. So 48 math choose 6 and enter. Okay. So you can do that on your calculator. Let's just go 1 decimal place. So let's just go 8.1 e to the negative 8, which you got to change. That's equal to 0.7 and an 8.1. And then to convert it into a percentage is going to go here. So the chance of winning the $1 million is 0.12345 zeros. Okay, and let's just for shits and giggles, let's see, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, trillions. So it's 81 trillion trillionth, not an S, trillionth of 1%. 81 trillionth of 1%. It's hard for people to imagine how tiny that number is. But when you write it out like that, because 1% is really hard to hit, right? 0.1% is hard to hit. 0.01% is hard to hit. 81 trillionth of a percent? Mind blowing. Okay, sorry. I drone on. Let me continue. Okay, I am going to tell you that this lecture today really, really does not lend towards very many you do situations because every single problem that I did today is very specifically cultivated for me to show a little different thing that you need to get from the nuance of the questions so you can understand. We might have one you do here at the end, maybe the last one. I think I'll probably be able to do the last one as a you do, but uh just hang in there. If you need a break, pause me. Take a break. Shoot, I'm going to pause you right now. I need a break, but I'm trying to get this done before mom gets up. Okay, so here we go. You might think, Dr. Kelly, this is the same question. This is not the same question. It's a different question. It says a certain state's lottery pays out $1,000 if 5 of their numbers match the 6 numbers drawn by the Lottery Commission. 5 of the 6 numbers. 5 of their numbers. If they get 5 out of the 6 numbers, you get $1,000. It's all that this is. Question's different. Okay? So we still need all of these things. Does the order in which they're pulled matter? No. All right, so we're going to still use the NCR. This is definitely without replacement. That is true for the total and the event. Okay, now let's go ahead and get after it. The total is going to be the same. It's the same situation. We have 48 numbers and we're choosing 6. That's still the same. Total number of choices. Okay, that's still the same. But what is going to change now is the event. And the event is, and I'm going to be really technical, the event is we get 5 of the 6 numbers. In other words, 5, let's see, 5 out of the 6 and then 1 remaining. I'm not fixing it. Remaining out of the 42 that are not of the 6 winning numbers. Okay, hopefully I didn't just like mumble myself into you not understanding what the event is. So here's the idea. The idea is that we're going to get 5 winning and 1 losing. Okay. So the probability of getting 5 of the winning numbers, well, the probability of getting 6 was 6 choose 6. So the probability of getting 5 is going to be 5. Of the 5 numbers, you only choose 4. Oh, I mean, sorry, 6 numbers. Of the 6 numbers, we only got 5, and then that is going to be multiplied. Of the 42 remaining numbers, we chose 1. Okay, and let me put a little note here. This says, of the 42 not winner numbers, we chose 1. Sorry about that. And here I'm going to put a little note also here that says of the 6 winning numbers, we chose 5. And I don't know what it is about this particular answer, or this particular problem, but it looks really, really confusing. But after you work it and see it, and I put those words down, and somehow it makes it kind of come together a little bit better. Anyway, here we go. Final kahuna here. So finally, we're looking at the probability that you win 1K, which is get 5 of 6 numbers, right? And that's going to be the event, which is 6 choose 5 times 42 choose 1 over 48 choose 6. And we're going to do all this in the calculator. Let me show you how it's going to go. Now notice we have more than one thing in the numerator, so I'm going to start off with a set of parentheses. I'm going to go 6 math over here. Choose 5, go up, close parenthesis, or you don't have to close parenthesis. Now we're going to just do the 42, or you can say times, might make you feel better, times 42. Hit math, go over to probability. 1, go back up, close the parenthesis, divided by, and then we can say 48. The math, go on over. The total was 6. All right, and we get this awesome number you're used to by now, 2 point, I'm just going to round it to 1 decimal place, so 2.1 e to the -5, still a very small number, but not nearly as small as winning all of them. That's going to be 0.1234521. And if we put our new decimal place in there at 0.0021%, we wanted to say that word out there. We've got tens, thousands, hundreds, I mean, 10, hundreds, thousands, 10,000. So 21 10,000ths of 1% chance. So here was the chance of 1,000 is 0.0021%. All right. Let's apply that kind of thinking to another problem here. Compute the probability of randomly drawing 5 cards from a deck and getting exactly 1 ace. Okay? So, does the order matter? No. Order doesn't matter, so we know Caro, NCR is the one. Is it with replacement or without replacement? It is always without replacement with cards, unless specifically expressed otherwise. So let's get our total here first. And total here is just the number of ways to deal 5 cards, basically. Okay, and so that is 52, because there's 52 cards, C, and we're dealing out 5. That's going to give us our total. Now, let's look at our event. Our event is, and let's break it down. Our event is, of the 5 cards we draw, we get 1 ace. So our event is dealt 1 ace. Okay? And so that, breaking it down like I did before, is going to be draw 1 ace. The probability that we draw 1 ace. And that we draw 4 non-aces. Because that's really what's happening here. We're going to draw aces and then we're going to draw non-aces. So what is a chance of drawing 1 ace? Well, there are only 4 aces to choose from, and we were going to draw 1. There's not 52 aces to choose from. We're just talking about the ace. We're not talking about all the cards. We dealt with all the cards with the total. Now we're talking about the event. And the event is that we get 1 of the aces and we don't care what the rest is. So this is getting 1 of the aces. So there's only 4 options. And then 4 non-aces. Well, how many cards are left? There are 48 cards, so 52 cards, and we draw out 4. There is 48. Choose 4. That's going to be our total here. 1 and 4 is 5. We're choosing 5 cards, and 48 plus 4 is 52. So everything is accounted for. So that's going to be our event. So let's see what our probability is. Probability that we dealt 1 ace is equal to 4 choose 1 times 48 choose 4. And all that crap is over 52 choose 5. And when we do all of that math there, we get a 0.2995, which is 29.95% chance of being dealt. Oops. 1 ace. All right, and I'm proud to say this is the last one. And I'm going to kind of do it here. We'll give a couple of minutes or so. But I encourage you to just pause right now, whether I leave some dead space or not. I encourage you to pause it and try to work this. And I'll give a little hint. The total is the same as the last problem, right? Because we're still drawing 5 cards from 52. And the event this time is draw 2 aces, draw 3 non-aces. So I'm going to leave you with that. Give about a couple of minutes. I'll go get my watch. I had to charge. So while you work on that, I'm going to give a couple minutes for you to think that through. Y'all really try. Don't just forward. Try. Think about it. Okay. All right. If you haven't finished, pause. Thank you. If you have finished, well, let's see how you did. Okay. So, drawing two aces. Of the four aces that you can draw, we're asking you to what's the chance we'll draw two of them. And there is still the same remaining 48 cards left, and now we're only choosing three. Okay, so let's see our probability of two aces is going to be 4, choose 2, times 48, choose 3, all over 52, choose 5. And when we crank that through, 0.0399, which is 3.99%. So basically is a 3.99% chance of being dealt two aces. All right. Thank you for hanging in there with me on this. I know it's dense. It really, really is. I'm going to encourage you to perhaps do your homework with my, oh, there's a crazy bug just come flying in my window. I'm going to encourage you to please do your homework as quickly as possible. Get on it, start messing with it, maybe even queue up this video so you can, kind of go along a little bit and see if you can find an example that will help you. I want to also tell you that there's a struggle involved here. And if you're not struggling, then you're not trying hard enough, or not hard enough. But listen, rarely is there anybody that's not struggling here. I wish I could take back what I said there, because that doesn't mean that some people won't struggle. But generally, this is a struggle topic. Just know that traditionally. But anyhow, y'all hang in there. See me if you need some help. And have a good day. Thanks.